Washington State University. Go Cougs!
The final component of activity learning that we will discuss in this course module is activity prediction. We have talked about how to extract features from sequences of sensor data, converting them into data points that we can use for activity recognition by learning a mapping from these data points to activity labels. We've used the data points for activity discovery to discover clusters or frequent sequences of these data points that could constitute activity patterns. And now we will look at activity prediction or forecasting into the future to determine what activities will occur and when. Consider the video that we showed at the beginning of the activity learning modules in which a resident entered the home in order to put away some groceries and do other activities as she would normally make part of her routine. We showed how we can extract the features from the data that's collected while she does these activities, and we also showed how we can recognize activities such as entering the home and putting away groceries. But in this case, can we predict what she will do next after what we see in the video? Predicting human activities is an important part of behavioral analysis. If we can forecast what activities will occur and when, then we can design systems that anticipate instead of just react to the current situation. As is indicated by these pictures, anticipating actions and activities allows us to provide timely automation that can potentially avoid disastrous results and can provide interventions that will promote and sustain healthy behaviors. By anticipating human activities, we can provide automated systems that turn on devices and adjust settings in order to meet the needs of the person when that activity starts. It is a difficult task to do well. It does rely on activity recognition as well as a number of other complex modeling techniques. In this module, we will separate prediction into two different problems. The first is, given a sequence of observed activities, as determined by activity recognition, for example, we will predict what activity from a set of possibilities will occur next. Second, we will look at the problem of predicting when a specific activity will occur again in the future. Let's start with the first problem, predicting the next activity. We will introduce an algorithm that's a type of sequence prediction, as you would find in other sequence prediction problems such as DNA analysis. We will use a history of observed activities to predict the next activity. So assuming that we have a sequence of activities that have occurred, the problem is to determine which activity is going to be next in the sequence. And the approach that we will introduce is based on LZ78 text compression. In addition to finding this process in compression of text, it's also used in compression of images, as is found in GIF images or PNG images. The process is a combination of using LZ78 to compress the history of observed actions that we have already gathered, and PPM, or prediction by partial matching, to determine the probability for every activity that it's the next one to occur in the sequence. So let's start with LZ78. With LZ78, we're going to parse a string into substrings. So given a string of symbols, x1, x2, and so forth, we're going to parse it into substrings or subsequences, which we'll refer to as W1, W2, and so forth. We're going to parse this input string such that all but the last character of a substring is equal to an earlier observed substring. And we will store all these substrings with their associated frequency information in a trie, which is essentially a tree structure that employs prefix matching. So this idea of a string in our case would correspond to a sequence of observed activities. And the reason that we're going to store all of them in this prefix matching type of tree structure or trie is that allows us to store all of the possible subsequences or phrases incrementally as they are observed in a sequence in real time. By storing the frequency information with each one of these subsequences, we can use that later on to perform probability calculations that, with the prediction by partial matching approach, lets us know which activity will have the highest probability of occurring next. As we mentioned, LZ78 can be used to compress a variety of different types of information. It's used to compress text. It's used in image compression. It considers any sequence of symbols. So while we're going to be using it for activity compression or compression of a sequence of activities, we can also use it for compression of a sequence of locations that a resident has visited in the home and therefore predict the next location. And this is also useful for automating a home or other type of environment. In this case, it allows us to visualize what LZ78 does when it parses a sequence of information. So in this example, we are showing a particular home layout and denoting each location of the home by a different symbol. C for this closet, D for a different closet, P for this bedroom, Q for another bedroom, L for living room, G for garage, and so forth. If we have ambient sensors in the home, we can collect information from them indicating the sequence of locations that a resident visited. An example observed sequence might be A, J, K, K, O, O, J, H, H, and so forth. What LZ78 will do will be to actually parse that observed sequence into phrases. And as it parses it, each phrase will be an extension of an earlier phrase that has been observed and stored in the trie. The reason for doing that is it allows LZ78 to generate these phrases incrementally in real time as the sequence is processed. Let's work through an example so we can see how this will work. If we consider a sequence of symbols, as shown at the top of the screen here, we are actually going to start to generate a tree structure or trie that corresponds to all the phrases that we observe in this sequence, along with the frequency with which the phrase has been observed in the input. This string can represent a sequence of locations, as we showed in the previous slide, a sequence of activities, or a sequence of what other types of information might be useful to process. The tree initially has a single node, which is just an empty string or an empty phrase. Every time that we look at the next part of the input sequence of symbols, we're going to navigate the tree top down, matching the symbols as we go, and incrementing the frequency with which that symbol or substring has been observed. However, each time that we look at a next string in the tree, we're also going to make sure that we're going to extend the tree by one symbol. It is easy to explain this with an example. So initially we have one node in the tree that just has nil or an empty string. The first symbol that we observe is an A. We can add to our nil tree a single node indicating a single symbol A with observed frequency 1. So this is a phrase and a substring that's been observed in the tree. Now that we've processed the first symbol, we can look at the next symbol. Now we could go ahead and visit the same node A and just increase its frequency. However, with LZ78, we don't ever just add to the frequency. We're always adding a new longer phrase to the tree as well. Therefore, the next phrase that we will consider is not just the symbol A, but a phrase that's long enough to grow the tree. So we can look at the next two symbols, A, A. On the left, we have our previous tree, and we will look at the sequence AA. With the sequence AA, we start at the beginning of the tree and look for a match of the first symbol, which we find with its child node. We'll go ahead and increment the frequency to 2 because now we've seen that phrase twice, but we will also grow the tree by adding a child node underneath this one, which indicates the phrase AA, and a corresponding frequency of 1. So this tree now shows that we've observed a phrase with a single A, frequency 2, and a longer phrase AA with frequency 1. The next symbol that we will consider is B. There is no path in the tree right now that corresponds to a single symbol B, so we will go ahead and add it as a child under the empty string with a frequency of 1. Now when we look at the next symbol A, we run into the same situation as before, and that is there is a child node here for A, and we can increment its frequency, but we never just increment the frequency. We're always growing the tree to include new, longer phrases. So we won't consider just A, we will consider AB, which is a new, longer phrase that we haven't seen yet. So when we look at this phrase AB, considering our previous tree, we will visit the child node A and increment its frequency to 3, and we look underneath it and there's not yet any node for B, so we go ahead and add that with the corresponding frequency of 1. So now this is indicated that we've seen a single symbol A, or single phrase A 3 times, and we've seen the longer phrase AB 1 time. If we look ahead now to the next symbol B, we can see that that phrase already exists in the tree, and we're going to continually grow the tree. So in addition to incrementing the frequency of the single symbol B, we will add a child node underneath it in order to represent the phrase BB. So we increment the frequency for B, we add a child node underneath it, and the frequency of the longer phrase BB is 1 so far. So hopefully you're getting the idea. The next symbol is B, which will not grow our tree, nor will BB, since we've seen that before. So we're going to have to consider the longer phrase BBA. So you can see with this incremental parsing that over time our phrases are going to get larger and larger. And intuitively, this gives us more and more context that we can use to eventually predict the next symbol in the sequence or the next activity. Longer context gives us more information, more routine behavior based on which we can make our prediction. So we will consider that next phrase BBA. This is our previous tree, and as we make our way down from the top, incrementing frequencies as we go, you can see that we will first visit this node B and increment its frequency to 3, and then visit the B underneath it because our phrase consists of a BB. We'll increment this frequency to 2, and then we'll add one more node underneath this for A with a frequency of 1. So this indicates that we've seen a single phrase B 3 times, the phrase BB twice, and the phrase BBA 1 time. Next, we'll consider the symbol A. Looking at this tree, we see we've already seen that phrase. If we extend it further to AB, we see that we have already seen that phrase. So we need to look at the longer subsequence, ABC, which is new for this tree. Based on the old tree, we can see we will first navigate to the A node and increment its frequency to 4, then navigate to the B node and increment its frequency to 2, and then add a C node underneath it with a frequency of 1. So our tree is getting larger as we incrementally parse this input sequence, which we're considering to be a sequence of observed activities. Although this could be any sequence, it could be a sequence of locations, or it could be an actual sequence of sensory events that were observed if we wanted to try to predict the next sensory event that would occur. Looking at the next symbol in the sequence, we look at symbol C, and that has not been observed as a single symbol phrase before. So that is a simpler example. We start with the root node of the tree, or the empty string, and there's never been just the single symbol phrase C, so we go ahead and add a child node underneath it with the symbol C and a frequency 1. The next symbol will be the symbol D, which has not yet been observed, so the same thing will occur. We will add a single node underneath the empty string with the label D and the frequency 1. Next, we observe D again, and because this single symbol phrase has been observed, we will not just increment the frequency, we will have to also increment the size of the phrase. So instead of just considering D, we'll consider DC. And if this is our old tree, we'll start with the empty string, then we'll visit the child node D and increment its frequency to 2, and then we'll add a node underneath it labeled C with a frequency of 1. We're getting near the end of our tree. The next symbol we consider is B. That has been considered before as a single node phrase. What about BA? That has not yet been parsed into our tree, so we'll consider the phrase BA. Looking at our previous tree and parsing the phrase BA, we would start with node B, increment its frequency to 4, and then add a new node underneath it labeled A, and since we've not seen this before, it'll be given the frequency of 1, BA with a frequency of 1. Next, we will consider symbol A, and that has been observed before, as has the sequence AA, but the sequence AAA is new. From our previous tree, the parsing would look like this. We would start at the root node, we would visit the child node A and increment its frequency to 5, as we see here. Then we'll go to the next level, which represents the phrase AA, increment its frequency to 2, and then eventually go and add one more node underneath it, representing the phrase AAA, and it will have a frequency of 1. Given that this is the entire history that we have observed so far of these symbols or activities, this is our final tree that we can then use to perform prediction.